The following video recording has been made possible by Symbotic, complete warehouse automation. From integrated supply chain consulting to fully automated picking systems with progressive financial models. Symbotic systems are deployed in major grocery, retail, and general merchandise operations throughout North America. Learn more at symbotic.com. And by Duchin Productions. Broadcast, corporate, and web video production services specializing in science and technology. Start the conversation today. Visit DuchinProductions.com to learn how video can get your business the customers, talent, and investors you've been looking for.
Hello everyone, my name is Roberto Tron, and today I'm going to talk about, so I put this title with vision-based localization and control, but really what I'm interested in, it's more like the subtitle of this talk, which is networks and geometry. So as Chris said, multi-agent systems are going to be everywhere, and the kind of multi-agent system that I look at are systems that include cameras. And why is important looking at this kind of multi-agent system? Because with multi-agent system, you can do things that with single agents cannot. For instance, you can cover areas that are much larger than the footprint of a single agent, or you can transport loads that a single agent cannot lift. And they are modular. So if you have multiple agents, you just put them together, and if one breaks, you just take it out, and the system should keep working. And why now is a good time to study this kind of system is because now we have networking is ubiquitous, so you can put network interfaces in very small agents. And you can also put pretty cheap but sophisticated sensor suite. So for instance, you can put cameras, IMUs on each sensor, and it's relatively cheap. And so there are different aspects that make this kind of problem interesting. For instance, planning for uncertainty or different tasks. But the aspect that I'm interested in is in seeing the interplay between the network topology of this multi-agent system and the geometry of the problem. So multi-agent systems typically are modeled as a graph where each node is an agent and where the edges represent interactions between agents. But each node also is a physical system, so it has some state which is embedded in some geometrical space. So for instance, each agent has a position and orientation. And the measurements also can be physical interactions or measurements between two agents. For instance, if you use cameras, you can get the relative rotation and translation between the agents. And talking about cameras, computer vision, now it's pretty reliable way to get measurements between sensors. And what can you do with computer vision? You can detect things. For instance, you can detect an agent as seen from another agent. You can match points between different pictures, and you can combine all these and estimate relative poses between agents or the agents and some object. But there are also some challenges. So for instance, detections most of the time are okay, but sometimes you get wild results. You detect something that is not there. And most of the times, if you have things that are really far away, computer vision really gives you very well directional measurements, but not so much distance measurement. And so you have essentially scale. Usually it's much less reliable than things like directions if you use vision. And so there are a few challenges. There are many challenges in multi-agent systems. The ones that I'm interested in that relate this network and geometry are how to coordinate these agents so that you have a global objective. So for instance, localizing the entire network with respect to a common reference frame, or trying to move the agents in a common formation, but just looking at local interaction. So for instance, the agent over here doesn't know what this agent over there is doing, but you still want them to achieve some global task. And the measurements might be incomplete. So as I said, maybe you don't have the distance between the agent, but you have really precise direction. And sometimes these measurements are wrong. So what I've been doing in my research is trying to tackle these challenges with distributed optimization, a tool called Rigidity, and how to get rid of wrong measurement, all by using the interplay between network and geometry. So regarding distributed optimization, this is to achieve a global task by local interaction. So you have this global task, for instance, achieving formation of agents. And how I formulate it is as you define a cost function, then they cause the task. For instance, the x's are the state of the agents, of the physical agents, and the UIs encode the relative position that they should have at the end of at the desired formation. And then you use distributed gradient descent. And the nice thing about this formulation is that you essentially apply distributed gradient descent and you automatically get a distributed algorithm for free, and with this kind of formulation. And if you pick your cost function well, for some condition you can prove almost global convergence. So you can start with your agents in strange position and they will converge always to the desired formation. And you have lots of flexibility. You can apply this in localization, formation control, with rotation, without rotations, with scale, without scale, and it's essentially just turn the crank and you get your algorithm and you can prove convergence. And so this is a simple result. For instance, these are a few pictures that represent the picture taken by a set of robots, and they match points, find the relative positions, and put them together in this global optimization, and you get a localization of the robots. And this for formation control, so you start from some initial formation, you want to achieve some desired formation by starting from some random positions, and again, looking at this global optimization, you can convert to the desired formation. However, there are some ambiguities. So for instance, if you just use vision and you don't have scale, then what happens is that, for instance, I found the localization, but in reality there is a global ambiguity that just from relative measurements, I cannot identify a global reference frame, so I can rotate my localization and it's still consistent with my measurement, or I can scale everything and I still get something that is consistent with my measurement. But so these are pretty intuitive, so like you can scale and rotate everything. But are there more? And the answer is yes, in some situations, and this goes under the idea of rigidity analysis. So, for instance, take a simple formation control task where you have each node represents an agent and each line represents visual measurements of just directions and not distance. So if you have this kind of graph, what happens is that I can take this triangle and move them along that line, and these configurations are all consistent with my measurements. So how to get around this? What I studied are methods to either, given your network, find a partition in sub-networks that each one is rigid, so that you know that you can essentially control the relative position of these agents and these agents, but not of the two groups relative one to the other. Or you can try to find new edges. So for instance, try to rotate your field of view to get new constraints so that you can recover rigidity. And so you can study ways to optimally select which edges should I add and how many I need. And it turns out that in both these analyses, cycles in the graph are key. And these cycles are key not just for analyzing rigidity, but also for getting rid of outliers. So why? So for instance, consider the problem of localization. In general, if you have a cycle in the graph and you try to compose all the rigid transformation along a cycle, you go from instance this position to this position to this position, and when you go back, you should close back to the identity. And this gives a very strong constraint. So for instance, if one of these measurements is completely wrong, then by analyzing the error that you accumulate along the cycle, you can realize that. And if you have many cycles, then you can try to do some inference and pinpoint exactly what measurements are wrong, just by using the fact, this interplay between the network and the geometry. Or for instance, when you are matching points between multiple images, sometimes you get inconsistent matching, so that if you go from here, 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 you should close back to if this measurement should close back here, but you get inconsistent, you're trying to match 2 points from the same image that physically doesn't make sense. And so I studied a solution on how to find out these kind of outliers and remove them so that you can get better estimation. And so, for instance, in the case of 3D localization, if you take these kind of pictures and you try to reconstruct a point cloud of the scene just from pictures, if you don't do this robust optimization that removes the outliers, then you get some results that are not always consistent. For instance, this piece of the wall doesn't connect with all the other, with the rest of the walls. But if you do this kind of robust optimization, you get a nice corner here, so it's much more consistent. And in the case of pairwise matches, these are what you get with just looking at pairwise matches between pairs of images without considering these cycle constraints. And the blue lines are all the matches that are wrong. And so you can see that if you take into consideration these global cycle constraints, then you get rid of most of these wrong correspondences. And this is just with the same data, just by exploiting the fact of this, the power of these cycles and combining network with geometry. So to conclude, I hope I convince you that there is a really nice interplay between network and geometry in these kind of applications that are computer vision driven. And the tools that are used are optimization, both centralized and distributed, and the notion of rigidity, and how to analyze it and improve it, and how you can use cycles and these cycle constraints to find outliers and get better results without any additional measurements. And going forward, what I'm looking at is how this notion of rigidity extends from simple systems where you have just points to more complex systems where you have dynamics and nonlinear constraints, and how to make distributed algorithms that can exploit these cycles constraints. And with this, I thank you.